So back in the day, somebody introduced you to the idea of BEDMAS in order to work out the order in which you should execute operations. BEDMAS was, of course, brackets, exponents, division slash multiplication, and then addition slash subtraction. Well, that's fine, but now that we're getting into more complicated functions, where exactly did square root fall into that acronym? Or ln, or e to the x, or sine and cosine. Those things didn't feature in BEDMAS because BEDMAS was intended for teaching algebra skills in grades 7, 8, and 9. And now that we're beyond that, we need sort of a new set of words in order to describe the pieces of functions that we need to work on. So in this particular example I have up there, there are 3 pieces to this. The first one, and the most important one, is the function itself. So in this case, the function that we're dealing with is the radical operator, so a square root. The next most important piece that's in there is this thing, and this part, everything that is inside of the function, is called the function's argument. And so that's 2x minus 3. And all the stuff that's on the outside is sort of the least important thing to the function. That's this and this here. These are external modifiers. So we have a multiplication by -5. And we have add 7. Okay, good. So what these pieces do is the function is really what determines the input-output. It decides what numbers can go in. Certain functions only accept certain numbers. For example, you cannot square root a negative number. So this function has decided that there's a certain flavor of numbers that it will accept, and then there's a certain flavor of numbers that it will output for you. So that's why this is the most important thing. It determines the shape of the function. It determines what numbers get spat out. The argument is the next most important thing because it's going to determine what numbers get fed into this thing. And I already pointed out that radicals can't accept negatives. So the argument there, that 2x minus 3, that's what determines if a number inside of here is negative. So this is why it's second most important, that the inputs are determined by this structure. Once you've determined the value of the argument and shoved into the function and gotten your answer, whether you multiply it or add something to it doesn't really matter anymore because the function has already done its job, and we're just tweaking the output. So these things get done last. So what we're going to do then is we're going to reframe BEDMAS in terms of these 3 bits. So the first thing you need to do whenever you're trying to reduce an expression, number 1, is you evaluate the argument. Okay, so you figure out what number is going to go into the function. Number 2, you execute the function. So if it's a square root, you square root it. If it's a ln, you push the ln button. If it's e to the x, you do e to the whatever and get your answer. Number 3, after you've decided what number's going in, you've executed the function, you modify appropriately. So you apply external modifiers. So that's your new BEDMAS. Evaluate the argument first, then execute the function, and then apply the external modifiers. And you must do those things in that order. So I'm going to take this function that we have here, and I'm going to actually evaluate it. So given f, I'm going to try and evaluate f at 11. Okay, so I'm going to put that number in there, replace all the x's with 11s. Okay, so my new order of operations here says that, oh, let's get this crap out of the way. Perfect. It says I'm supposed to evaluate the argument first. Well, that's this chunk here. So, the BEDMAS stuff still applies, or we haven't thrown it completely out the window. We've just enhanced it a little. So I should be doing the subtraction first. 11 minus 3 is 8. And then 8 minus 2, or 8 times 2 is 16. So if I evaluate that argument, I end up with 16 inside my function. So once, well, check. I have evaluated the argument on this particular expression. Next thing I'm supposed to do is execute the function. So I have this 16 sitting inside of a square root. So I'm going to square root 16. The square root of 16 is 4. Okay, check. I've executed the function. Now that the function's been executed, I can apply those external modifiers. So negative 5 times 4 would be negative 20. And negative 20 plus 7 would be negative 13. Therefore, the function at 11 is negative 13. So if you went all the way out to an x value of 11 on a sketch of this function, the y value would be at negative 13. Good. So I'm going to erase this. I'm going to leave this chunk up there so we can follow these steps. We'll do 2 more examples and it's off to the practice problems. All right. So we've got a ln in there, which you haven't done much work with. It was just introduced in the last unit. But it's just a button and it should follow these same rules. So I'm going to try and evaluate this function when x equals 6. So in it goes 2 ln 3 6 plus 4 minus 10. So my new order of operations says I should evaluate the argument first. So I find everything that's in the ln, that's this stuff. And I have to get that done. So 6 plus 4 is 10, and 10 times 3 is 30. So this thing reduces to 2 ln of 30 subtract 10. Good. Finished. Now it says I'm supposed to execute the function. So I have ln 30 sitting there, so I'm going to have to pull out a calculator and type in ln of 30, and it gives me 3.401 plus some more decimal points, but I'm just going to keep 3 just so it doesn't get too messy here. So g at 6 would be 2 multiplied by 3.401 minus 10. Check. I have executed the function. Third step is to apply those external modifiers. So I take that 3.401 and I double it. That gives me 6.802. And 6.802 subtract 10 gives me negative 3.198. Approximately. So you'll notice that even though it looked like it said 30 minus 10 here, you couldn't do 2 ln 20 because that would violate these rules. It would have meant that you started applying external modifiers before you executed the function. So be very careful about that. Everything like this, when you have a number to fill in, you must evaluate the argument first. Once you have the argument done, you apply the function. Once you have the function applied, then you can apply those external modifiers to get your final answer. So one more example and then off to the problems. So this one looks a little different just because of the notation. It's got a 5 sitting over top of something, which looks like a fraction, but this maybe will cause you less stress. There were never such things as fractions. There were only rational expressions. So I'm going to rewrite this so that it looks like all the rest of the functions we've had. We pull that 5 out in front. And then I'm going to use negative exponent notation to pull this thing out of a fraction. So it doesn't look like a fraction at all. It would be h of x equals 5, 2 times x minus 7 to the negative 1 plus 3. And if I do that and use better penmanship, there we go. I've taken this thing that looked like a fraction and I've written it as something with an argument, a function to apply, and 2 external modifiers. So when you see expressions like this, if the fraction causes you heartburn, you may want to choose negative exponent notation in order to make it look like all the rest of the functions. So now that I've done that, I'm going to show you how to evaluate one of these. So h, let's do this at h at 9. So in goes the 9. So step 1, evaluate the argument. I have to find all the stuff that's in there. That's this chunk of things. And I have to get that done. So 9 minus 7 is 2, and 2 times 2 is 4. So my function here would be 5 times 4 to the exponent negative 1 plus 3. All right, now, next step, once that's done, is to evaluate or execute the function. So 4 to the negative 1, you could type that directly into your calculator and it will give you 0.25. So that's an option. Or you could write that as 1 over 4. That's an option as well. I'm going to use the fraction option because ultimately we should be moving towards fractions. So h9 is, that would be 5/4. So the function has been executed. Actually, let me slow down. I skipped a step there. That would be 5 times 1/4. Now the function has been executed. If I apply this external modifier, 5 times 1/4 is 5/4. And 5/4 plus 3, I will need a common denominator. So 5/4 plus 3, there's 4 quarters in each, and there's 3 of them. That means a total of 12, which gives me 17 quarters. And 17 quarters is 4.25. So if you use the -1 button on there and rendered this as 0.25, 0.25 times 5 gives you 1.25, and 1.25 plus 3 gives you 4.25. It's the same answer. I would prefer the fraction, and if you are pursuing a career in engineering or physics or mathematics or finance or anything like that where it's number heavy, you need to prepare yourself for that because fractions are the expectation because they're superior in their answers. There's no rounding, there's no errors. That's the best way to write your number. If you'd like, if you're not confident in your fraction skills yet, do it both ways. Do it as a fraction, do it as a decimal, and then make sure that they match at the end. So the practice problems have a whole mix of things from the different functions. They have sines and cosines, they have parabolas, they have cubics, they have rationals, radicals, exponentials, and logarithms, which are the 7 base functions that we're going to work with. But all 7 of those functions follow the same 3 sets of rules. You must evaluate the argument first, and then you must execute the function, and then, only then, do you apply the external modifiers.